This video is on the pH scale. Now we've already talked a little bit about acids and bases and what they are and the definitions, but now we're going to talk about a scale or a numeric value that can tell us if it's an acid or a base and kind of changes within that what they mean. So the pH scale we first need to understand is what tells us if something is an acid or a base, or how acidic or basic something is. So pH scale, how acidic or basic a substance is. Okay, so this is a log scale. So it goes from 0 to 14. 7 right in the middle here would be neutral. Anything less than 7 is an acid. Anything greater than 7 is a base. And the closer you get to neutral, the less acidic or the less basic it is. The further away you get, the more it gets. So closer to 0 would be more acidic. Closer to 14 would be more basic. Oops. All right, so this is a log scale, which you maybe have talked about in math, and it's a base 10 scale. So if all you're going to have to know for this class in terms of logs is that whenever you go from like a 1 to a 2, for example, you're increasing not by 1 on the pH scale, you're increasing by a factor of 10. Because pH stands for percent of hydrogen. So this is how much hydrogen you have. So this will make more sense when we do some examples and talk about the equation. But let's kind of just write this down. That a change of 1 on the pH scale equals a factor of 10 in the H plus concentration. Okay, and then I'm going to write this down below later, but I'm going to write it here also. The pH, the reason we're talking about H plus concentration, factor of 10, log, all that stuff, is because pH equals the negative log, right, and this is base 10, we don't usually write it, of our H plus concentration. And what you'll find here is that your pH and your H plus concentrations are inverses of each other. So as your H plus concentration increases, that means your pH will decrease. Because as your pH decreases, you're getting more H pluses because, right, you're going towards 0, which is more acidic. So the more H plus you have, the more acidic it is. The less H plus you have, the more basic or anything higher it will be. Okay, so pH is dependent on temperature. So different temperatures will give you a different pH value, even if it's the same substance. The ones in this chart up here, and basically all charts that we normally talk about and use, are at temperatures of 25 degrees Celsius. This is about 77 Fahrenheit, so it's a little warmer than like room temp, but this is what's called standard ambient temperature. Okay, so we talked about standard temperature is 0 Celsius, standard ambient temperature is 25. All right, so I'm going to write that equation again. pH equals negative log of our H plus. We don't normally write the 10, it's assumed. And we talked about how H plus and H3O plus are the same, so you might also want to think about this as being negative log of H3O plus. Now, what if you want to solve for H plus? You either have to understand how to do algebra with logs, or you have to remember this, that H plus then would be 10 to the negative pH. So let's do some examples with this. Okay, so if H plus is given as a 1 times 10 to the negative third concentration, so that would be moles per decimeter cubed, calculate the pH. Okay, so pH equals negative log of our H plus, which we have right here. So I'm going to plug this in as a negative log of 1 times 10 to the negative third. All right. So here's where you have to know how to use your calculator. So Some of your calculators, you'll have to push the number first and then push the log button. Some you'll have to push the log button and then the number. Negative might be beginning and end. It kind of depends on your calculator. So I want you to play around with this in practice, and we can go over and check this in class as well. But the answer here would be 3. Okay, so the thing is, we're going to write this as 3.000. So a couple rules with this, like how do I know how many sig digs, digits, all that kind of stuff. Okay, so 2 big rules. The number of sig digs in your concentration equals the number of decimal places in your pH. All right, so here we have 3 sig digs, which means that here we have 3 decimal places. Okay, the 0.00, right? 1, 0, 0, 0, 1, 2, 3. The other thing is, kind of when in doubt, or just checking with your pH, you should always have pH should always have at least 2 sig digs. So basically you should not have whole numbers for pH ever. All right, so let's do another one now. Given our pH, let's find the H plus concentration. So you can do this algebra with logs, or like I said, you can just plug this in. So you can say, well, let's see, H plus concentration is 10 to my negative pH. So I'm going to plug in 10 to the negative 8.67, and I want you to actually type this in and get a value here. And what we have here is our pH has 2 digits after the decimal, 2 decimal places. So our H plus concentration is going to be 2 sig digs. So when I type this in, I get 2.4 times 10 to the negative 9th moles per decimeter cubed. Make sure you practice typing these in so you kind of know how to use your calculator. All right, so a little bit further, and let's relate this a little bit to stuff we've done before. So auto-ionization or dissociation of water. If you have 2 water molecules, what can happen is an H can get transferred from one to the other. Because remember, water can act like an acid or a base. So what you can get is you can get that H3O plus and you can get the OH minus. So this can turn into an acid and a base. All right, so why do we care? Well, what we care about is that our equilibrium constant for this could be then our H3O plus concentration times our OH minus concentration, and that's our products over the reactants. But in this case, our reactants are both liquids, so they are not included in your equilibrium equation. So we could also write this as just H plus, just to simplify, times OH minus. Okay, why do we care? Well, we care because this is what's called our ion product constant for water. Anytime you have H plus concentration times OH minus concentration, you will always get 1.00 times 10 to the negative 14th. All right, and this can help us solve for one or the other. So knowing that, let's say I know H plus, and I can solve for OH minus because I know multiplied, they will equal 1 times 10 to the negative 14th. All right, and I'll show you that in a problem as well. All right, so what else does this tell us? Well, it tells us that if H plus and OH minus are equal to each other, you'll have a neutral solution. Because the only way to get that is, and we could do the algebra here if you want, but if we had, let's see, H plus and OH minus were the same, so that'd be X times X. That would give us 1 times 10 to the negative 14th, right? X times X is X squared. So if we square root both sides, right, X, or that concentration, would be 1 times 10 to the negative 7th. And that's the concentration. So the pH would be negative log of 1 times 10 to the negative 7th. Type that in and you're going to get a pH of 7. So that's that neutral solution. So pH equals 7 if H plus and OH are equal. This should make sense. You don't have more acid, you don't have more base, you have the same, so it's right in the middle. Now, what if you have more H plus? Well, H plus is going to be more acidic. So this is when your pH is going to be less than 7. If you have more H minus, that OH minus, that's going to be basic, and that's going to be where your pH is greater than 7. All right, so other scales related to this. So you can also have a POH. This is the percent of hydroxide. So it works the same way in that you're going to get, it's going to be the negative log of the OH minus concentration. And what it's going to give you is it's going to give you a kind of reverse scale of this. Okay, on the POH scale, I'm just going to do this. All right, so POH, this would be 14, this end, and this would be 0. Okay, you have the same scale with 7 in the middle, and it'd still be, you had more OH minus, right? You're still going to be more basic. More H plus, you're still going to be more acidic. Okay, it's just an inverse scale. All right, so that means something also when we get to this. If it's an inverse scale and pH and POH are added up, they're always going to add up to 14. So if I go back to here, right, 14 right here plus 0 is 14, right? What would this be? 13. 13 plus 1 is 14. This would be 12, etc. Okay? So let's kind of just summarize all of these. All right, kind of put it all together. All right, oops, I'm going to add one more thing to this. We could do the reverse for this OH minus, right, would equal our 10 to the negative POH, just like our pH. Okay, so let's summarize the whole thing. Find some space. You could go to your, like the opposite side too in the summary space if you'd like as well. It's up to you where you want to put this. All right, so we've got kind of 6 main equations. So first we'll start with this. The pH is the negative log of your H plus concentration. The reverse of that, your H plus concentration, is 10 to the negative pH. Okay, so then we also have the POH is the negative log of our OH minus concentration. So then our OH minus concentration is 10 to the negative POH. Oops. Okay, so now these are related to each other. If I have the pH and the POH, if I add them up, or if I know one of them, I can find the other because they will always add up to 14. If I take the H plus concentration and I multiply by the OH minus concentration, they will always multiply out to 1 times 10 to the negative 14. All right, so these are our equations. We will use these more and do more practice in class. And we'll talk about kind of what you get in the data booklet and what you don't, but feel free to look at your data booklet and kind of see, like, what do you get and what do you have to know how to find.